Okay, so I want to say a few things about summation notation, things that we encounter that look like this. The sum as I goes from 1 to 5 of x sub I. That's how I would read that. What is that equal to? It is equal to x1 plus x2 plus x3 plus x4. So all we've done is we've taken this x term and we've substituted in values for I, starting with 1, ending with 5, and we've added them up. Okay, so the this big Greek letter here, that's a capital sigma. Sigmas are often used to denote sums. And we often encounter these summation notation when the endpoint is kind of arbitrary. Okay, so often we'll see things like the sum as I goes from 1 to n of xi. Same deal, it says start at the starting value that's down here below the sigma. So it says 1, we start at 1, we go up to 2, we're going up just by adding 1 each time. 3, whatever. We don't know how many because we don't know how big n is, but we do know that when we get to n, we stop. Okay. We get to our last value, that's the end of the sum. Really nothing more to it than that. We're not doing anything different mathematically than we would be if we would write things as a regular sum with plus signs. We're just writing them a little bit more compactly. The fact that we're writing the sums more compactly has its pluses and minuses. It has its advantages and disadvantages. If we're writing the same thing over and over again, it is really nice to be able to abbreviate a little bit. And I think that is the main reason why people use summation notation, but it makes them harder to decode. And so anytime you find yourself looking at summation notation and getting kind of a freaked out feeling, like there's a lot going on and you're not sure what it is, believe me, you are not alone. Most people feel that way at some point. Most people also, once they get past feeling that way, will become comfortable with using the notations. But when you're in that situation of, wow, there's just, I don't know what that thing means, the response should be what we did here. Just write out the sum in the regular way. So let's do that with an example here. So if we have the sum, we'll use slightly different letters here as j goes from 1 to m of -2 to the jth power. Okay, so what our x sub i's are in this example is that they are powers of -1/2. So we're going to start with -1/2 to the first power, because that's what the summation symbol is telling us here. So we'll add the 1, even though that's kind of superfluous, plus -1/2 to the second power, plus -1/2 to the third power. When do we stop? We stop when we get to -1/2 to the nth power. Okay. If we want to simplify that a little bit, we could actually substitute in for those powers. -1/2 to the first power really is -1/2. -1/2 to the second power is positive 1/4. The negative times the negative gives us a positive. -1/2 to the third power, -1/8. Okay, so we're getting a picture of powers of -1/2, and we're going to end at this. We don't know what that is because we don't know what m is, but it would be true for any value that m could take. Let's do one more example. What else do I want to do here? Let's do this one. I equals 1 to n of I to the power -2. Let's just write that out. Okay, so now what our x sub i's are is they are actually that I, that index number, being raised to the power -2, which means like we're squaring it, we're putting it in the denominator, right? Negative exponent means that we're putting the power in the denominator there. So we've got 1 over 1 squared, there's my I equals 1 term, plus 1 over 2 squared, plus 1 over 3 squared. Again, I'm sort of getting the picture here, all the way up to 1 over n squared. And so each time, when I equals 1, I've got I to the -2 power. When I equals 2, I to the -2 power. I to the -3 power, keep going, keep adding them up until we get to I to the -n power. Okay. So that's really all there is to summation notation. No new things here. It is really just addition. And because of that, the algebraic rules are just the normal rules that we have for adding up numbers. But they look a little different. So let's see what they look like when we're using this notation. So factoring works the same way it does with summation notation. So if we have something like the sum, I goes from 1 to n, okay, times x sub I. Okay, so what I've got here is I've got the x's, which have the I subscript there, and that's indicating that as I is changing, x is changing. But I've got something else here that's not changing. K is just staying the same. There's no k sub I. Yeah. So what does that equal? Well, it equals k times x1 plus k times x2 plus k times x3. Okay, we get the picture all the way up to k times xn. Fine. If I see this sum, I'm going to use the distributive property and I'm going to factor out that k. I'm going to say that it's just equal to k times x1 plus x2, blah, 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 all the way up to xn. Oh, and look at that. I might rewrite this guy using summation notation. Okay, let's do it that way. So it's k times the sum as I goes from 1 to n of xi. Okay. So something that you will see, we'll be doing it in 200A. I use this kind of algebraic logic a fair amount. Starting with a sum like this, we can factor the k outside of the summation. And the reason why we can do it is because it's not changing as I changes. Another thing that we can do is we can change the order in which we add up our terms. We could do that a couple of different ways. Okay, so one thing is if our x sub i's, the thing that we're adding up as I goes from 1 to n, are themselves sums. Okay, so say what we're adding up is xi plus yi, or some more complicated thing that fits into that general form. I'm going to claim that that's just the same thing as adding up the x's as I goes from 1 to n, and adding up the y's as I goes from 1 to n, and then of course adding them together. Okay, well let's write that out. See if that looks up. Okay, so if we have x1 plus y1 plus x2 plus y2 plus x3 plus y3. Yeah, we're getting the picture here. It goes all the way up to xn plus yn. So that's, I've just written out this side of my my equation there. Yeah, commutative law of addition says I can do the x's first, have x1 plus x2 all the way up to xn, and then I can do the y's after. Sorry about that. Where'd my equation go? Here's where I want to be. So where I was before my screen started jumping around there is I'm claiming that we can take this kind of sum and split it up into two smaller ones, and I was just writing out the sum in the without summation notation to show you how that works. So here we have the x's and y's added together. So x plus 1, x1 plus y1, x2 plus y2, we're letting the index go there. And I can just rearrange that to have first all of the x's, x goes from 1 to n, and then all of the y's, y goes from 1 to yn, and that indeed is the sum as I goes 1 to n of xi plus the sum as I goes from 1 to n of the yx. Okay, one other way that I might want to split up sums would be according to the index. So if I'm just adding up anything we want, any xi's, that goes from 1 to n, it's perfectly fine if it helps me if I'm doing some algebra and trying to simplify. If it's helpful to first add up from letting I go from 1 to m, the xi's, and then starting with I goes from 1 to m plus 1 all the way up to n. I can do that. I can let m be any number less than n that I want. So just doing an example of that, let's let n equal 5. If I have the sum as I goes from 1 to 5 of the x of i's, sure enough, that is the same thing as letting I go from 1 to 3, adding those x of i's, and then separately letting, sorry about that. Separately letting I go from 4 to 5 for the last two x of i's. So here I'm saying add up all 5 terms. It's the same thing as saying first add up the first 3 and then those last 2 that you didn't have before. Okay. Finally, just a couple of facts about summation notation, a couple of things that are, again, nothing mysterious here, but can be a little bit puzzling. One thing that sometimes will come up when we're doing algebra is we might have the sum as I goes from 1. Let's pick a number here. Let's say just a number from 1 to 5 of x, not x sub I. Okay. So what I'm saying here is we're adding up. We might say that we're just adding up a constant here. This x is not changing as I is changing. Okay, so what does that equal? Okay, when I equals 1, x is x. When I equals 2, x is still x. And when I equals 3, it's still x. And when I equals 4, it's still x. You get the picture, okay? That this equals 5 times x. And regardless of how many things we add up here, I goes from 1 to n of x is n times x. We wouldn't normally write nx that way, but sometimes in the process of simplifying something, we can get a term that looks like this, and then it's easy to simplify as just nx. The last thing I want to point out, we saw a hint of it in one of our examples before. When we have summation notation and we're seeing powers of -1, what that's telling us is that the sum is going to be something where you've got sign switching. So let me just show you what I mean here. We have the sum as I goes from 1 to n of -1 to the power I xi. Okay. What that is saying is, okay, when I equals 1, -1 is -1, so we have negative x1 plus when I equals 2, -1 squared is +1, so it's plus x2. When I equals 3, it's an even power of -1, so it's negative x3 plus x4, etc. If you might be thinking, oh, well, what if we want the negative signs on the even parts of the sum? No problem. We can just adjust the expression. We can go, I go from 1 to n of -1 to I plus 1 power xi. And so that would give us when I is 1, I plus 1 is 2, so x1 is positive minus x2 plus x3 minus x4. Okay, so the main message of this video really has been that the summation notation is very dense notation. It is always a good idea, if you're a little bit uncertain about it, to do what I've been doing throughout. Just write out a few terms, see what they look like. You'll get a sense of that there.